In the next clip, Corrado Malanga mentions the existence of an entire city underneath the pyramids.
Scopriremo che lì sotto c'è una vera e propria città, tra virgolette. Siamo, come profondità, a circa 1200 metri.
You know, a very, very, very small number, which represents an improvement over known SAR resolution by 5 million times. Actually, it goes 5 to even 50 million times better than what known SAR satellite imagery can do. Are there massive alien-like engineered structures under the pyramids on the plateau of Giza in Cairo, Egypt? Two researchers recently said they have discovered something using SAR, Synthetic Aperture Radar doppler tomography, and that these structures are incredible engineered structures that extend kilometers down from the base of the pyramids down into the earth. Just look at these images that they've shown in their press release on the 15th of March this year. And then they had a conference the following day. We're going to look at their papers. We're also going to look at their press conference and some of their claims. And in this video, what I wanted to do was try to explain what they claim they've done. And then we'll analyze what they've said. We'll also look at what they've said in their press release. So here's the introduction from the press release.
L'ingegner Fiippo Biondi, specialista in tecnologia SAR, e il dottor Armando Mi, esperto di egittologia. Grazie alla tecnologia SAR o radar ad apertura sintetica, combinata con la nuova metodologia della tomografia doppler, il gruppo di ricerca qui presente ha fatto una serie di scoperte senza precedenti, localizzate sotto la piana di Giza. Questa innovazione tecnologica consiste nel convertire le informazioni radar fotoniche in segnali fononici. Questo permetterebbe di esplorare strutture sepolte in profondità sotto la superficie terrestre.
Parlare?
All right, so the three researchers are Corrado Malanga, Fiippo Biondi, and Armando May, who's an Egyptologist. Malanga is from the Department of Chemistry and Industrial Chemistry from the University of Pisa in Italy. Fiippo Biondi is from the Department of Electronic and Electrical Engineering from the University of Strathclyde, Glasgow. And I'm not sure where Armando May is from. He's an Egyptologist. But before we look at SAR and the technique that they used, or the methodology that they claim that they've used to detect structures kilometers down into the earth using radar, I thought it would be helpful to ease us all into these types of applications with technologies that you're familiar with. So just to whet your appetite, look at this ultrasound here. This is an ultrasound showing a little baby girl I think it's 5 months old. This is very hard for me to tell if there's a girl there. Can you tell if it's a boy or a girl? I cannot. It's very hard for me to determine what sex that baby is. But if you look at this picture, this is also an ultrasound using a different machine, a more modern machine which uses a little more sophisticated sensors and signal processing. This is what it looks like now. Now the colors have been added artificially. But this is also an ultrasound images that's been signal processed to create a picture like this. And this looks more like a baby to me. You can even tell if it looks like mom or dad. So that gives us an impression of what can be done with modern computers, with signal processing. And it's just unbelievable what engineering has been able to accomplish. Other types of non-invasive detection methods to find things under the earth or inside of bodies that are not visible and not using surgery or digging are, for example, airport metal detectors. Every one of us have been through them at our local court or when you go through airport security. And they use the same technology that you essentially have for handheld metal detection. And what this basically is, it uses a coil of wire or several coils that is pulsed with a sensing circuit to detect the inductance of the coil. Now, these airport security or the human scanners have multiple coils in them. And when there's a metal that passes through the field in front of this coil, it changes the magnetic field. And so that will change the inductance, and that can set off an alarm or give you an idea of how large and what kind of metal that is. Another technology that everyone is very familiar with is X-ray technology. And X-ray uses simply X-rays that can pass through a human body, and some of the rays are absorbed by certain types of tissue and material in the body, like bone will absorb more of the rays than other types of tissue, and so you can detect that on the photographic plate on the other side. A CT scanner uses X-rays as well, but it is electronically detected, and then signal processed to construct three-dimensional or two-dimensional images of the cross-section of the body that's been scanned. Nuclear magnetic resonant imaging is engineering wizardry. This is a fantastic technology which uses the principle of the polarization and alignment of hydrogen atoms with a large magnetic field. So there's a huge, this is not a CT scanner, it's a completely different technology. It almost looks like identical, but it's different. So here we have a massive superconducting coil, which is kept at a low temperature to keep it superconducting. And this coil contains a large current, and the large current then produces a massive magnetic field, a DC field or a static magnetic field, which is, once this thing is turned on, it runs forever while that temperature is maintained. And the hydrogen atoms in the water molecules in our bodies, and our bodies is full of water, bone, tissue, muscle, tendons, everything, our brains, everything contains water. The hydrogen atoms in the water molecules will align with the polarization of that magnetic field. And if you then pulse the body with another magnetic field, every hydrogen atom will bounce out of alignment with the original large DC field. And when it bounces back and forth, as the exciting field is collapsed, it bounces back in alignment and generates another field that can be picked up with a pickup coil. The resonant part is simply a way to isolate what you want to measure. And so in layman's terms, what's happening is you collect all those data, all those signals, and by passing that in a very clever way through signal processing algorithms, we can reconstruct the image of what the body is, what the body inside looks like, where it's actually the concentrations of hydrogen that we're looking at. But you can now see tissue and bone and tumors and other things, artifacts inside the body. Absolutely amazing technology. So what about sonar? Sonar is another one. Sonar is very familiar, used in the Second World War to hunt down the German U-boats, the submarines, that were basically torpedoing the Alliance's boats and ships from America and Britain. And so sonar was used to hunt these sea wolves. And it's essentially just a vibration that's sent out in the water. It's a shock. It's a mechanical or acoustic shock wave that's sent into the water, and the reflections or echoes are measured. And this can then be used to deconstruct and figure out what it saw. Now, modern signal processing and computers are much more sophisticated than what was available in 1945. So now we have fish finders that operate on this principle. The ocean floor is being mapped using sophisticated sonar. We can also find shipwrecks and wrecks of airplanes on the ocean floor or on the bottom of rivers, lakes, and so forth. Then there's LiDAR, which is similar to radar, but this time it uses lasers. Light detection and ranging is LiDAR. Then there's radar, which has been used for decades to track aerial aircraft. And then, so if you understand what how Doppler radar works, then you will have an idea of how ground-penetrating radar works. The instrument looks more like a push lawnmower, but it's not. There are no blades. What this is an antenna that shoots an electromagnetic pulse down into the ground at a certain frequency. And again, the echoes are measured with the coil inside of the same instrument. And the instrument, as the instrument is moved, it also keeps track of its exact position. And if all that information is passed through signal processing algorithms, we can get an image of what lies underneath inside the ground. Now, ground penetrating radar does not go very deep. I think the deepest I've seen it go is like maybe 25 meters into the ground. But it's very dependent on the characteristic of the ground. So if it's a bedrock, or if it's rock or soil or sand, anything that is conductive, like moisture, will limit the depth and attenuate the wave faster. So if there's iron particles or copper or aluminum or something like that inside the ground, or silver, these are all conductive materials that will make it harder for the wave to penetrate. Similarly, if there are magnetic materials, paramagnetic or diamagnetic materials or ferromagnetic materials inside of the ground, then that will also affect what the wave what you can measure with and how deep you can go with ground penetrating radar. But now let's get to SAR. Let's get to synthetic aperture radar Doppler tomography. Instead of a push lawnmower that measures beneath the Earth, these are airbound antennas, either on airplanes or on satellites, that shoot these electromagnetic pulses down towards the Earth. And they are used typically to measure surface topography. So you want to get echoes from the surfaces of what's on the Earth, whether it's a ravine or a mountain, or whether there's a structure, or let's say a canopy of tree lines. And you're going to get a three-dimensional image of what the topography looks like. And again, it's the having an accurate knowledge of data of the position of the sending satellite, and getting then the information from the signals with knowledge of how far the satellite is above the Earth, and with fairly sophisticated signal processing, you can get detailed images like these. This is the website of the Capella Space satellite system, where some satellites are using SAR technology to collect signals that can be used to produce highly accurate three-dimensional images of the topography. Now, what do these researchers claim? So let's take a look at some of their papers. The first one I want to look at is a paper written by Fiippo Biondi, and it's entitled "Scanning Inside Volcanoes with Synthetic Aperture Radar, Echography, Tomographic Doppler Imaging." And this paper is from 2022. It was published in the DPMI publications Remote Sensing Journal. Okay. And this is just Fiippo Biondi. And he explains here that what they do is they use this synthetic aperture radar signals from the satellites to collect vibrational data. So he has some clever math here to try to qualify what they are doing. But this block diagram essentially explains it. So they take an SAR image, they pass it through a digital Fourier transformer, they then pass it through some filters to extract the noise level data, which they claim has enough information about vibrational information, background vibrations on the surfaces of, in this case, the volcano. This then gives us seismic waves raw data, which they pass through a fast Fourier transform to collect a tomographic map, which gives them in-depth geolocation of, using a tomographic filter, of what's going inside the volcano. So let's take a look at this paper that Fiippo Biondi wrote with Corrado Malanga in 2022 together, and it's called Synthetic Aperture Radar Doppler Tomography Reveals Details of Undiscovered High-Resolution Internal Structure of the Great Pyramid of Giza. So this deals with a different pyramid. This is not the Khafre pyramid. This is the Great Pyramid of Giza. It was published in MDPI, particularly the Remote Sensing Journal. Okay, and I'm going to read just from this abstract. A problem with the synthetic aperture radar, or SAR, is that due to the poor penetration action of electromagnetic waves inside of solid bodies, the capability to observe inside distributed targets is precluded. Under these conditions, imaging action is provided only on the surface of distributed targets. The present work describes an imaging method based on the analysis of micro-movements on the Khufu pyramid, which are usually generated by background seismic waves. The obtained results prove to be very promising, as high-resolution full 3D tomographic imaging of the pyramid's interior and subsurface was achieved. Khufu becomes transparent when observed in a micro-movement domain. Based on this novelty, we have completely reconstructed internal objects, observing and measuring structures that have never been discovered before. The experimental results are estimated by processing series of SAR images from the second-generation Italian Cosmos Skymet satellite system, demonstrating the effectiveness of the proposed method. So then the introduction goes through a bunch of New Age ideas and conspiracy theories and just hand-waving about the pyramids themselves before they actually says anything about what they did. So let's take a look at what they say here at the end of the introduction. They say, in this paper, we use a new method based on the tomographic reconstruction of micro-movement with the aim of performing imaging of the principal targets that make the main internal structure of the pyramid visible. We use the similar methods already experimented in another reference they have, to search for cracks in large infrastructures, but not for tomography. The physical principle we use is that of estimating the vibrations captured by the Khufu pyramid during the SAR observation time interval. The vibration estimation is completed by evaluating the Doppler centroid anomalies, which is an indispensable parameter that is used during the SAR azimuth focusing process. We use Doppler sub-apertures to estimate the vibrations present on the pyramid. The vibration energy is generated from many sources, such as wind. A great contribution in terms of vibration energy is also generated by the city of Cairo, which is located closely to the pyramid of Khufu, and by the presence of the Nile River. So here you see that they are basically using the vibrations that they think they can detect from the SAR signals that were reflected off the surface of the Earth and these pyramids. Okay. And then if you go down to the methodology, so they say in this work, the micro-movement method technique is used to perform sonic imaging by processing a single SAR image in a single-look complex or SLC configuration. The technique involves the micro-movement estimation belonging to the Khufu pyramid and is generated by the background ripple underground seismic activity that affects superficial vibrations. The micro-movement estimation is completed through MCA and performed in the Doppler direction. Multiple Doppler sub-apertures, SAR images with lower azimuth resolution, are generated to estimate the vibrational trend of some pixels of interest. The infrachromatic displacement generated by Doppler centroid anomalies due to target motion and acceleration is calculated through the pixel tracking method or technique using high-performance subpixel co-registration. Okay, so if you go down here, you will see images explaining the technique exactly from the previous paper that I showed with about the volcano. Here we have a SAR signal that they claim this is the vibrations that they extract, and they claim vibrations here that go to a 1 times 10 to the minus 7 meters. So let's talk about resolution. In the paper, this graph and these blue graphs show the vibrational information that they have isolated from the SAR images. So what they are doing is they're taking 1 pixel in the SAR data in time and collecting the vibrational information from that 1 pixel that they isolate, and they look at different times and then pass that through filters to collect the noise, basically, which they claim has this vibrational data in it. Now, first of all, the satellite is, let's say, between 500 and 700 kilometers up in orbit above the surface of the Earth. The vibrational displacement that they are measuring here, they show to a maximum and minimum amplitude of +1 and -1, 10 to the minus 7 meters. 10 to the minus 6 meters, or 1/1,000,000th of a meter, is a micron. So they're talking about the maximum amplitude you see on this graph is 0.1 micron. If you want to have any resolution here, you will have to go down to 10 to the minus 8 meters, or 1/100th of a micron. Okay, so if we just want to look at the vibrational data fidelity of 10 to the minus 8 meters, or 1/100th of a micron, versus the satellite's distance away from what we're measuring. And let's say the satellite is 500 kilometers up in orbit. That's 500 times 10 to the 3 meters. So if we look at the fidelity divided by the distance, we get 2 times 10 to the minus 14. A very, very, very small number, which represents an improvement over known SAR resolution by 5 million times. Actually, it goes 5 to even 50 million times better than what known SAR satellite imagery can do. So let's take a look at what the SAR satellite people themselves say. And for this, I'm going to go to the Capella website. I'm going to go here to this article. It's called Full Resolution SLC Imagery, Revolutionizing Commercial SAR Data. And this was published by Capella Space on October 1st, 2024. And here they speak about a breakthrough that they had. There was apparently, the government had regulations on how they could take data and how many times they could look. And so they were limited. The regulations were limiting their satellites. They couldn't basically get to their full resolution. And all companies that had satellites in space were limited to about a 0.5 meter resolution. This is 50 centimeters, okay? 50 centimeters or 500 millimeters or 500,000 microns. That is the maximum resolution that they could accomplish, the best resolution. They couldn't get any smaller. But thanks to the lifting of some of these regulations, they were able to get to their theoretical full resolution of 5 centimeters. Okay, so I'm just going to zoom in here so you can see that. So this is what they are talking about. At the time, all SAR imagery produced by US companies were restricted to no better than 0.5 meter resolution, thus limiting what Capella was able to provide to our global customer base. Therefore, even when our imagery was collected with a 23 to 43 second spotlight during a 16-degree synthetic aperture, Capella was required to form single-look SLCs using only 1/9 of the collected data. These regulations were recently modified, allowing Capella to deliver our single-look SLCs at the theoretical full resolution of 0.05 meters, maximizing the available information to users in all product types. So 0.05 meters is 50 millimeters or 5 centimeters. This is incredible if you think about how high that satellite is, right? And you can look at these. The limiting factors are, among others, scattering characteristics, system noise during the collection, right? These are the limitations of that resolution. Position knowledge accuracy, because there's inaccuracy also in knowing where your satellite is, and the quality of the autofocus method. Okay, so these 4 factors influence the accuracy of the data that you receive: scattering, noise, position accuracy, and focus accuracy. Okay. In another article that they wrote, here's an article called Debunking SAR Myths by the same company, Separating Facts from Fiction. And here, among that, they have myth number 2, SAR can see through buildings. This myth likely stems from SAR's remarkable ability to penetrate clouds, smoke, and vegetation. However, SAR cannot see through solid structures like walls or roofs. Instead, it interacts with surfaces, bouncing radar waves back to create detailed imagery of exterior surfaces or features like building outlines, roads, and landscapes. Okay. And then there's the same mathematical derivation and justification that they showed in the previous paper, similar images. And if we go down here, you'll see that there is a simplified block diagram. Again, you have the single SAR image, which they pass through filters to extract the noise, basically. And then they do this pixel tracking complex displacement estimation to come up with an acoustic map of what happened on the surface of these pyramids. And then we can look at, all these images that they generate, or they claim to generate, of things that are happening inside the pyramid after they've done their signal processing on these. They claim they can collect. They can collect images of features deep inside the pyramid from the noise. In this introduction, they said they used synthetic aperture radar, satellite imagery, and doppler tomography to turn photonic radar data into sound and into vibrations. And that's what we were looking at when we were looking at some of the images. Okay. So what they claim to do is they are able to take the satellite data, these satellite images, these satellite signals that are actually used for surface topography. They are using that data to eliminate the surface perturbations, but looking at the noise. It's basically the noise level signals inside those SAR data that they are using to collect vibrational information from background seismic vibrations generated by the Giza or Cairo, the Nile River, noise that are coming from external sources that vibrate in these pyramids, on the surfaces of these pyramids, and that the satellites pick that up. And so they can isolate, they pass the signals through bandpass filters to pick up the acoustic vibrations. And from the acoustic vibrations, just like ultrasound, they are then able to reconstruct what is happening deep inside the Earth. That is the claim. I want to point out that when you have a probe, an ultrasound probe that collects data about a baby inside of a womb, the precise position of the probe must be known. That's producing the acoustic, the acoustic signal. It's a vibration that's sent in, and it collects the echoes. But then the probe's position must be known in order for the signal processing to work and get these accurate images. In this case, the satellite is known, but the origins of the acoustic vibrations are background noise. This is not from the satellite. The satellite is picking up topographical information. Let's listen to some of the things they say in their press conference. The first clip I want to play for you is one of Corrado Malanga speaking and telling us about the satellites that are about 680 kilometers above the surface of the Earth in orbit, and where they collect that, where they turn the photonic information into phonomic information. You'll have to read the captions because this is in Italian.
A circa 680 km d'altezza, in orbita attorno al pianeta, che trasforma i segnali fotonici in segnali fonomici, cioè trasforma la luce in suono, in vibrazione. Tutto quello che noi possiamo quindi vedere è un'immagine sonora delle cose che andiamo a vedere. Questa tecnica ci permette di guardare dentro le cose. Come voi sapete, i fotoni.
So they claim that they turned light into sound, into vibrations, and then they create sound images from radar images. The next clip, he mentions that several images are needed to construct these 3D images. It requires hours and hours of staring at these images to construct the 3D images.
Questa è un'immagine presa da un altro punto di vista. Bisogna avere sempre gli stessi oggetti posti da un'altra angolazione e bisogna che la consapevolezza di queste immagini entri dentro di noi, e questo si può fare solo guardando queste immagini per ore, tornando indietro a riguardare le vecchie tomografie, tornando a riguardare quelle nuove, cercando di identificare ogni struttura in modo tridimensionale. A questo punto potevamo costruire alla fine un modello tridimensionale delle nostre ricerche.
In the next clip he uses computer algorithms and artificial intelligence to reconstruct the images into 3 dimensions. And artificial intelligence is always right. They don't make mistakes.
2 strutture di questo genere che sembrano, quando li guardate per la prima volta non riuscite a capire di che cosa si tratta, sono in realtà 2 scatoloni, 2 grosse scatole giganti che scopriremo poi hanno circa come dimensioni, le dimensioni di 80 metri di lato, 2 scatoloni di 80 metri di lato. Non è un fenomeno di paraedolia, come si potrebbe immaginare, ma è lo stesso computer che ci dice: guardate, sono fatti così gli scatoloni. E il computer, con le sue analisi, con l'aiuto dell'intelligenza artificiale, ricostruisce questi 2 scatoloni, come vedete qui, in cui entrano in ogni scatolone 4 dei tubi che partono dall'alto e scendono verso il basso.
In the next clip, I want to show you these images that they show. This is at 648 meters. Can you see the spirals and the wells in these images? I cannot. Sorry, cannot. I guess I'm not qualified.
Siamo ad una profondità di 648 metri, solamente a questo livello. 648 metri. Guardiamo come apparivano alla nostra tomografia i tubi che, li vedete come sono fatti, qui sono 8, sono in, diciamo così, posti su 2 file al centro del lato lungo della piramide, e vedete che sono, si vede bene, circondati da qualcosa che sembra una specie di scala a chiocciola che scende. Questa scala a chiocciola noi l'abbiamo ricostruita sostanzialmente così. Vedete? Sono due scatoloni in cui in ogni scatolone scendono 8 tubi, fino a 648 metri, 4 da una parte e 4 dall'altra.
In the next clip, Corrado Malanga mentions the existence of an entire city underneath the pyramids, underneath all these structures.
Tutta questa roba luminosa che vibra. Quando noi andremo a fare, e domani lo mostreremo, degli ingrandimenti, scopriremo che lì sotto c'è una vera e propria città, tra virgolette. Siamo, come profondità, a circa 1200 metri.
In the next clip, Corrado Malanga claims that they used the data from 2 satellites. These are synthetic aperture radar signals, but they see sound reflections.
Vi ricordo che noi abbiamo utilizzato 2 satelliti, non uno solo, quindi i 2 satelliti ci danno risposte completamente coerenti, quindi tutto ciò che potrebbe essere un riflesso sonoro, noi lo sappiamo identificare perfettamente, perché un riflesso sonoro che vediamo su un satellite e sull'altro non c'è, perché l'altro satellite sta da un'altra parte e quindi vede le cose in un modo completamente differente. Va sottolineata un'altra cosa. Nella nostra ricerca,
in the next clip, he claims that they used the Capella and Umbra space satellites, and that they got the data for free, that anyone can download this data, and that the research cost nothing.
I 2 satelliti che abbiamo utilizzato, che sono Capella Space e Umbra Space, ci forniscono i dati gratuitamente. Tutti possono recuperare questi dati, basta andare sul sito di questi 2 gestori e scaricarsi i dati. Quindi questa ricerca non è costata niente. Lo dico perché a paragone di altre metodologie.
So what I decided to do is I wanted to look at the data that he claims they used. And so let's go there. This is the Capella space satellite, SAR satellite website. You can see the satellite here. There's a video of the satellite moving across the Earth. This is probably a computer-generated image or video. But this is indeed SAR images can be generated using this data. And this satellite system is in existence. It's used by NASA, by commercial, by military companies, by private companies, and even by individuals. So they use SAR, and they can come up with fairly sophisticated, very detailed images of the topography of the Earth over which these satellites moved in orbit, very high in orbit, 680 kilometers, I believe. And indeed, the data exists. You can download some of the data samples that they have in a catalog. And indeed, they also have data of the Giza Plateau. So we can go to Giza, and you can indeed look at the data that they have for the Giza Plateau. There's Giza. There's the Giza Plateau right by Cairo. So the Giza pyramids are in this area here. And you can indeed download the Capella data, SAR data. And it costs you nothing. So in the next clip, Corrado Malanga says that this is an innovative technology that allows you to look deep inside the Earth by downloading data from the internet, without visiting the place. You can do it from your computer. You don't have to go to the monument. You don't have to go fly there. Don't have to deploy expensive equipment because the data has already been collected. You are simply collecting data and you can pass it through their software. He says there are still many problems to sort out. He says the research is not finished, but previously he said it was free.
Sostanzialmente, mentre la nostra ricerca dura un anno, pochi mesi, sostanzialmente il tempo di verificare tutte le decine e decine di tomografie fatte da più satelliti, il tempo macchina necessario per fare gli accumuli, trasformata di Fourier, dice così, di tutte queste cose, sicuramente non sono gli anni, i soldi, la tecnologia, le persone che sono necessarie per scoprire 1/10 di quello che noi scopriamo con questa tecnologia. Quindi questa è una tecnologia innovativa che permette di guardare dentro i monumenti antichi senza andarci, senza spostare una pietra, conservando quindi questo che è il bene, senza alterarne la forma e la struttura. Ci sono a questo punto tutta una serie di problematiche.
In the next clip, Corrado Malanga says something which is another huge red flag for me, because when we have research that is novel, new, innovative research, innovative methodology that is supposed to be a breakthrough, it first has to be validated independently, objectively by another team. We have to validate the methodology or the theory. We cannot just accept it by someone by someone's word. And this is part of the scientific method. But listen to what Corrado Malanga says, because we know this has not been peer-reviewed. We know it has not been validated or done by or repeated by anybody else. So nothing has been. The method hasn't been validated, and yet they use this unvalidated method to proclaim they made a breakthrough in what they find on a finding. They find something extraordinary using an unvalidated method. That is suspicious, to say the least. But listen to what Corrado Malanga says here. He says there's no need to verify the results. He says we only took pictures. He said just like if you take a picture of the Tower of Pisa, you don't need 500 other people to take pictures of the Tower of Pisa to know that there is a Tower of Pisa. He says what we did, this research shows what there is under the pyramids. That's what he says. You don't need anybody to verify this. That is highly suspicious. That is what a scammer would say.
Il risultato è questo. Ci sono delle cose. Vedete, questa ricerca non è da comprovare. Non è che si deve aspettare altri tipi di lavori o altri scienziati che la possano dichiarare vera, perché sono fotografie. E io fotografo la torre di Pisa e non è che c'ho bisogno che altre 500 persone fotografino la torre di Pisa per dire esiste la torre di Pisa. Quindi questa ricerca, già così com'è, prevede che questi dati siano reali. Ma questo cosa vuol dire? Vuol dire che qualcuno ha costruito qualcosa a 1200 metri di profondità in Giza. Vogliamo credere che siano stati ancora gli antichi egizi?
The next clip, he says that this will rewrite human history and we need to scan the entire Giza Plateau.
La necessità di portare avanti questo studio è evidente. Perché? Perché la storia mi sembra che debba essere riscritta e questo sarà in effetti il programma che noi ci porremo, perché la piana di Giza va scannerizzata totalmente per vedere esattamente cosa c'è là sotto.
In the next clip, he says the wells are void. They are empty wells. And also these spirals are empty spirals that go around the wells.
La cosa fondamentale è che questi pozzi sono in realtà dei tubi, cioè dentro c'è il vuoto e sono tutti uguali. e sarà molto improbabile che si tratti di qualcosa che è stato fatto dalla natura.
But in the clip that follows, he says these structures were used to support the pyramids that couldn't stand on their own, and that they would have sunk beneath the sand if it wasn't for these structures, except these wells are voids.
Una ipotesi di lavoro è che alcune di queste strutture servano per sorreggere la piramide, perché abbiamo fatto dei calcoli statici e abbiamo visto che la piramide di Khafre pesa un sacco e per tenerla su ci vuole una base perché se no scende nella sabbia, cala. I calcoli fanno vedere che sostanzialmente in migliaia di anni queste strutture sono scese di più o meno mezzo metro. I costruttori evidentemente hanno previsto che non si può costruire una piramide sulla sabbia e allora sotto è necessario costruire dei pilastri.
Then he starts claiming that the builders had knowledge of vibrations and electromagnetics, and that these vibrations were used to cure the pharaohs of diseases.
Allora forse capiremo che noi ancora non abbiamo. L'idea nostra è sostanzialmente legata al fatto che gli antichi, chiunque essi fossero, avessero una forte consapevolezza e coscienza di che cos'è la fisica dei fononi e non dei fotoni, cioè del campo elettromagnetico. Noi siamo fissati sui fotoni, sulla luce, Maxwell. Bene, questa gente, secondo il mio modesto punto di vista, sapeva lavorare sulle vibrazioni. Tanto è vero che nei primi lavori, cioè nel lavoro pubblicato su remote sensing, questo noi lo diciamo, attribuendo alla struttura della piramide di Cheope il funzionamento di una macchina infrasonica che, muovendosi con il vento, producesse attraverso quelle strutture a Z, voi le avete viste qui, 5 piazzate praticamente in serie, in parallelo, producesse una certa vibrazione che curasse il faraone.
So, a lot of problems with this research. But here are a few points that I think we need to just go over. First of all, MDPI, this journal in which these papers were published. If I go to this paper here, we look at MDPI. You can investigate, you can look at MDPI yourself. It's a highly questionable journal. It's not a journal with proper peer review. There's no peer review here. This is just fake peer review. It is a very questionable journal. And if you wanted to publish it into a truly scientific journal where you would have actual peer review, it would fit into two journals in particular. The IEEE Transactions on Geoscience and Remote Sensing, which has a peer review process, and those peers who will review are experts in your field. So they would be experts in remote sensing, using SAR and whatnot. They would know their stuff. The other journal where you would publish this is the IEEE Transactions on Signal Processing. But they did not publish anything in either of those journals, which tells me if they tried, it was rejected, or they know it would be rejected because it's not actual proper research. So there's no article in your IEEE Transactions. And your IEEE, the Institute of Electrical and Electronics Engineers, is the largest professional organization and has proper peer review. Secondly, then the next point is that they banned and blocked researchers who asked pertinent questions on Facebook, on their Facebook page. They just block them. Instead of answering questions of when the researchers ask questions about what they did, they block those questions. Their papers and their conferences were full of new age ideas and questionable conspiracy theories. So they were referring to things that are non-existent and not scientific. So this is highly unprofessional. Then they used an unvalidated method to make an extraordinary new discovery. That new discovery cannot be validated because the method they used hasn't even been validated. So nothing here has any substance until the method has been validated against known discoveries before, known data. You first, before you can go and make an extraordinary claim of what you discover using a method, you must validate the method. And to validate the method, you would go and deploy the method on something that's known to show that the method works. Here's a box with a ball in it. I'm scanning it and I can see the ball. I know that I can open the box and I can see there's a ball inside of it, right? For example. Or go to a place where they have made excavations, they've dug things up, scan that and show that cavity, show what's inside there. And then we'll believe you, then we'll take you seriously, and then have someone repeat the experiment who understands it and do it, and then we'll know. That's not been done. But they make this massive discovery about things deep under the pyramids using a method that is questionable, that remains very fishy. So they should validate first before making extraordinary claims about new discoveries. Then Malanga says, but look, nobody needs to validate this research. Nobody needs to validate this research. Really, Malanga, that is really suspicious. That puts you down in the, scammer category as far as I'm concerned. Then my question is, why is this research presented in such a convoluted way? Why isn't it clearly presented? They are both researchers. They are at the universities. I'm talking about Corrado Malanga and Fiippo Biondi. I cannot say much about the third researcher. But this means that they have teaching responsibilities, and a teacher or professor is supposed to be able to take a complicated topic and break it down into simple steps so that students can understand it. Now, when you do research and you write papers, you're also supposed to be teaching your academic peers or what you are doing so that it can be validated and scrutinized and perhaps, either shown that it's valid or shown that it's not valid, that it's invalid. To expose weaknesses, to expose the limitations of it or the strengths of it. And that is how science moves forward. But in this case, the way this work is presented in their papers that I have up here, or in their conferences, it's presented in such a convoluted way as if it's pseudoscience, meta-science, just not valid scientific methods at all, anywhere in the process. The presentation, the paper, the methodology, the way they present it. The papers do not contain the limitations of their method. It doesn't tell you what the assumptions are. It doesn't speak about the fact that they are basically extracting noise from signals and then reconstructing that noise and extracting actual three-dimensional images going hundreds of meters, kilometers down into the earth from noise that they get from satellites that are, hundreds of kilometers up in orbit. So nobody who is a scientist are going to fall for this. It is absolute nonsense. And they don't even present their work in bite-sized chunks to teach other experts on what they are doing. They are compressing a lot of technology. They are compressing into a paper. Both papers are like that, without breaking it down into bite-sized chunks. Normally, if you do research, then you are going to break it down into bite-sized chunks, and you're going to publish something that first tells you the story of the first part of it. Then you're going to get to the next level. You're going to publish a new paper. You're not going to publish everything together in one paper and try to obfuscate the weakness of it and make it hard for people to follow. You're going to make it easy to follow. You're going to teach your peers how to do it, and they did not do that. They're trying to hide the weaknesses of it, and they're trying to basically bamboozle the scientific community and the public with this. That's my claim. That's what I see. That's what I think. There's no conclusive data to validate the method from known artifacts. They did not do that. these papers fail to explain and convince the reader that this synthetic aperture radar data has enough fidelity to extract acoustic vibrational information from it that can be used in any signal processing. There's no evidence for that. There's no convincing. There's no argument for that. Then their data, the papers that they've written about the Great Pyramid, the Great Pyramid, and what's inside of the Great Pyramid, those cavities do not replicate the artifacts that were found using other methods. So the Great Pyramid, which is not the Khafre pyramid, by the way, this is the pyramid that they spoke about in the first paper that I shown. That data doesn't correlate. It doesn't agree with known artifacts inside the pyramid, and that's been collected by other methods, ground penetrating radar, muons radiation, with all the other methods that's been already deployed into the pyramid, in the pyramids and around on the Giza Plateau. Their findings don't contain that. It doesn't correlate. So why not? Then they say the research took only a few months. This research was quick. It was easy research to do. You just sit in your computer, download some data, and you do some signal processing on it. Then you pass those signals, those noise that you collect, that you filter out. You filter out all the noise, or filter out anything that's not noise. So you just keep the noise, basically. And then you pass that through a signal processing algorithm. And then you give it to artificial intelligence. You say to artificial intelligence, what do you think is here? Does this look like a well? Yes. Does it look like a spiral? Yes. That's what they did. They basically take noise, give it to artificial intelligence, and ask artificial intelligence to generate beautiful pictures that they then publicly announce is findings underneath the pyramid. That is not research. That's not science. Sorry. And so finally, my final observation about this is, since the research is free, this finding is as good as it is worth in funding. This is as good as that. And the amount of money that should go to these researchers for this finding is equal to what they spend on this research. That's my conclusion on this. Free, nothing, zero. And the amount of confidence we should have in this research is exactly equal to how much this research cost. It was free. It cost nothing. So do not have any confidence in it. Do not spend any money on it. Do not reward these researchers with anything more than what it cost them, which is nothing. That's my conclusion. As Truth Matters Unplugged, investigate. Thanks for watching. See you next time.